evening, everybody. My name is Leslie Lowe's, and I'm the lead outreach coordinator for the Galileo project. And we want to welcome you to this very exciting evening we've got planned for you today. It's celebrating the discoveries that the Galileo spacecraft has made while it's in orbiting Jupiter for the past almost 2 years now, and looking forward to 2 years more. We have a real special guest tonight to tell you about what we've been learning, and that is our project manager, Bill O'Neill. But before we do that, I want to make sure that everybody's pretty up on what they know about Galileo. So what we're going to do is have a little Galileo lingo quiz. And my lovely assistant in the back is going to pull up our first question, which is, if something is Jovian, it is very happy, quite upset, or something having to do with Jupiter. Any guesses? Very good. Oh, we have a hot audience tonight. All right. Number 2, the word... Oh, let's wait for her to get, okay. The word satellites can refer to telecommunications satellites, military spy satellites, Galileo the spacecraft, a planet's moon, or all of the above. All of the above. You should wait for all of the answers before you yell it out. I heard somebody say C. Okay, number 3. Now this one you got to concentrate on really hard. The 4 Galilean moons are Io, Edward, George, and Chelsea, Idaho, Europa, Georgia, and Colorado, India, Egypt, Ganymede, and Canada, or is that Kenyatta? Irvine, El Monte, Glendale, and Callisto. No one's yelling out yet? Okay. And it is Io, Europa, Ganymede, and Callisto. And they're called Galilean after their discoverer, Galileo Galilei, in 1610. First saw them as little discs of light and realized that they were moving around Jupiter, much like you saw tonight if you got a chance to be out at the scopes. All right. Now about the Galileo spacecraft and mission. The orbiter is a lunar lander, a manned spacecraft, the part of the Galileo spacecraft that's orbiting Jupiter. C is the correct answer. You guys were hesitating. We're getting into harder questions. Oh, gotcha. Okay. This one has 3. The probe is a medical device invented by Galileo, a high-powered telescope, or the mini spacecraft that detached from the orbiter and entered Jupiter's atmosphere. Oh, what an audience. Again, with number 6. Number 6, we are moving on to a 3-answer possibility. G8 refers to a gate on a California license plate, a space on a bingo card, or Ganymede 8, a close flyby of Ganymede on Galileo's 8th orbit. Great. Let's see, we will do 2 more. DSN stands for do something now. Don't say never, or the Deep Space Network. C. Very good. A DSN is a set of antennas that we use to communicate with Galileo and the other spacecraft that you've been hearing about lately. There's one each in Australia, well, that we use, California and Spain. Near Barstow. There's one that you could go visit. And then finally, in Galileo lingo, playback refers to Galileo's retribution, playing games behind the backs of project managers, or playing back data on Galileo's tape recorder. That's right. Originally, we were planning to send our stuff through our high-gain antenna live, and then we had tape recorder problems and we had to use it, and now so we play back through our low-gain antenna. And you'll be hearing more about this when I introduce our project manager, who I am very happy to have with us tonight. Bill O'Neill got his BS degree in aeronautical engineering from Purdue with distinction in 1961, and he also has a master's in the same field from USC. He worked at Boeing and Lockheed before he joined JPL back in '63. His assignments at JPL have been specialties in spacecraft navigation and also in designing missions. He's done trajectory design and navigation for Surveyor, which was the first soft landing lunar spacecraft. And then he was the navigation chief of Mariner Mars 1971, which was the first U.S. spacecraft to orbit another planet. And then the navigation chief for Viking, which was one of the first soft landings on Mars. He also was the manager of the JPL Mission Design Department. He served as the Science and Mission Design Manager for Galileo during the time when the mission was being developed. And then in February of '90, Bill was appointed to be our Galileo project manager. As such, there have been a number of firsts that have happened with regard to Galileo, but I'm going to leave those for him to tell you all those exciting things. He's also been honored with NASA's highest award, the Distinguished Service Award Medal, and the Purdue Distinguished Engineering Alumni Award, and an honorary doctorate from the University of Padova, Italy, Galileo's university, Galileo Galilei's university. So there's a nice rounding and connection of things here. So without further ado, what I'd like to do is let Bill take over and describe to you the wonderful findings we've been having, and thank you again for coming.
Thank you, Leslie, and thank you all for coming. It's wonderful to see such a turnout as this. I have to say that years ago I could not even have dreamed of standing here under such glorious circumstances as we now have. We did it. Project Galileo is a stunning success. A week ago Sunday we completed the final encounter sequence of the primary mission. All 10 of the orbiter satellite encounters have been grandly successful. And it's doubly rewarding because the project team overcame the greatest engineering challenges ever faced by a planetary mission. We have written not only scientific history, but also engineering history as well. And in the next 30 minutes, I hope you'll see what I mean. And Leslie has only allocated me 30 minutes, so I have to cover 20 years in the space of 30 minutes, so we'll get right going here. The one thing we really should take care of is that it's well past time to put a smile here, I think. And maybe we could dim the room lights a little bit. This is Jupiter. That's not a blemish. That's the Earth, to the same scale as Jupiter. Earth would fit inside Jupiter 1,400 times. 2/3 of all the mass in the solar system outside the sun, that's the size of Jupiter. So Jupiter contains 2/3 of that mass. So imagine taking up all the other planets, including Saturn and Mars, all of them, you would only have half the mass that Jupiter contains. To further impress upon you the magnitude of it, there's that image of Earth again. It would fit inside the Great Red Spot about 3 times. The magnetosphere of Jupiter, the region in space that's controlled by the magnetic field of Jupiter, it's the largest object in volume in the solar system. It's 100 times the volume of the sun. And deep inside this magnetosphere, we have 16 known natural satellites. And I'm delighted to tell you that there, in fact, are 17 known satellites, the 17th being the first artificial satellite of Jupiter, the Galileo orbiter. Now, here are the Galilean satellites, the 4 major moons, Io, Europa, Ganymede, and Callisto. And compared with the size of our own moon and the planet Mercury, in the upper panel, we see the circular orbits of these satellites in oblique views to the scale, to the size of Jupiter. And in the system, we measure things in terms of Jupiter radius. So from Jupiter to the first orbit, Io's orbit, is about 6 Jupiter radii. Interestingly enough, it's about the same distance as from our Earth to our moon. But Io goes around every 42 hours instead of once a month because of the tremendous gravity here. Europa is at about 10 RJ, Jupiter radius, and it completes the circuit in a half a week. Ganymede at 25 Jupiter radii, at 15, completes one in a week, and Callisto at 25 in 2 weeks. They're all locked in rotation around Jupiter. Just like our moon always presents the same face to the Earth, these always present the same face to Jupiter. Now, to further illustration, here are those 4 Galilean satellites compared to Mars. Ganymede, the largest moon in the solar system, that satellite Jupiter is 3/4 the size of Mars. And here also compared to Titan, Earth, and Venus, and our own moon. Now, most of you know that when Galileo discovered these moons in 1610 and said, oh, Copernicus is right after all, and reported that to his customers here, the church, they were very upset. In fact, he got house arrest out of it. This expression is quite familiar to us. We saw that a lot from NASA headquarters when we were trying to get launched. But I'm happy to tell you, we finally got this straightened out once and for all. In January, the project scientist Torrance Johnson and I presented to Pope John Paul II an album of our best images at that point, and the Pope was very impressed. But obviously, you see, we bypassed the guys in red and went right to the main man. The project, from inception, has had 3 co-equal scientific objectives: investigate Jupiter, the satellites, and that magnetosphere. This is a photograph of the atmospheric entry probe. Galileo was the first and only spacecraft to deliver an instrumented probe to an outer planet. This photograph was taken at Kennedy Space Center just before encapsulation for mounting in the orbiter. This is the parachute that it descended on. This is the antenna that sent the information from the probe's instruments up to the orbiter. This is a cartoon of the Galileo spacecraft, and I invite you all to look at the full-scale model in the next room later on. I could spend a day, of course, talking about this, but I cannot, only a few minutes. Here, notice that the probe, its aeroshell, was carried in the belly of the orbiter. Galileo is, in many respects, the most capable, most sophisticated planetary spacecraft we've ever flown. And I say that because it's the only dual-spin spacecraft we've ever flown, among other reasons. Everything above this interface, from here on up, continuously spins, both for stability but also equally important to provide a continuously rotating platform for the fields and particles instruments, of which we have 6. Below that interface, we have our D-spun section, spin bearing on the center line, and motors that drive exactly at the same rate as the upper section spinning, but opposite direction. So this is 3-axis stable. So we have the best of both worlds. We have a 3-axis spacecraft here and a spinning spacecraft here. On the D-spun portion, we have our 4 telescopic instruments, including the camera that you'll see the images from. We also have a remote sensor on the spinning section, just one, for a total of 5 remote sensors. Here's the propulsion system. This is an international project, very, very much so. The Federal Republic of Germany designed, built, and supplied the propulsion system for Galileo free of charge to the U.S. government in order to participate in the scientific mission with a total of 3.5 German instruments on the spacecraft. Most of our electronics are housed here in this electronics bus. This magnetometer boom extends 11 meters from the center line out to the tip. And this is the high-gain antenna that did not deploy, and we necessarily have to do all of our communication over a low-gain antenna here at the tip of the mast. Now, the progression in getting to Jupiter was nothing short of amazing. The project was started 20 years ago. In October of 1977. And at that time, we were going to launch in January of 1982, just 5 years later, on a so-called three-stage interim upper stage in the shuttle. Very shortly, within a couple years of start, it was announced that this would never be ready in time, nor would the shuttle. So we were moved to an 84 launch, and because the opportunity was not as good performance-wise, the geometry of Earth and Jupiter, we had to split the probe and orbiter into two separate launches and plan to build a separate carrier spacecraft. So we're going to have two launches on the shuttle with two of these three-stage inertial upper stages. Shortly after that, it was determined that this was no good either, and that we would save a lot of money by putting Galileo back together for a single launch on a Centaur that would be specially developed, a high-energy cryogenic rocket for the shuttle to use up all the shuttle lifting capability, and that, in fact, would allow us to go on a direct trajectory with the whole spacecraft back together. And, in fact, it was in late 81 that it was determined, NASA determined that this was not affordable, and all we could use was the two-stage IUS. So we then planned to launch in May of 85, and JPL would build a kick stage to help get the energy, but we would still, in that case, have to go around the sun in a 2-year orbit, much like we did, and get a gravity assist from the Earth 2 years after launch in order to make this work. And it would not have given us 10 encounters. At best, it would have given us 8 encounters in the Jupiter system. But in fact, in the summer of 82, the Congress told NASA that they never intended that this be stopped and that this should be reinstated. We had by then lost enough time that we had to slip to an 86 launch, but of course the developers of this General Dynamics Convair had worked along pretty much, so it was only a 1-year slip in plan. And in fact, Galileo, orbiter and probe, were at Kennedy Space Center along with this massive new upper stage rocket being prepared for a May 86 launch when the Challenger exploded in January of 1986. And to make a long story short, in the wake of that accident, it was determined that this high-energy stage was too dangerous to carry in the cargo bay. So once again, we were told this could not be used. And in fact, in July of 1986, we had no way whatsoever to get Galileo to Jupiter. In fact, the only trajectory we knew would work was one to the Smithsonian Institution, which of course was not what we wanted. Then the trajectory designers here at JPL worked a miracle. They found a most counterintuitive way to use this two-stage IUS, which had already been flown many times, it was already flight proven, to get Galileo to Jupiter. This stage normally could only get Galileo as far as Venus or Mars, nowhere near Jupiter, but they came up with a remarkable solution to the problem. So after that, I think you can appreciate how delighted, what an ecstatic experience it was on October the 18th of 1989 when we launched on the Shuttle Atlantis. We were just so anxious to get out of town, and this was wonderful. We had a perfect launch, and we had a perfect deployment of the upper stage rocket with Galileo attached from the shuttle, as you see here. This is the limb of Earth. And this remarkable, sometimes I even refer to it as a crazy trajectory that got us to Jupiter. The idea was, at launch, don't put the launch energy into speeding up in order to get out to Jupiter. Go off in the wrong direction. Put all of the launch energy into a retro maneuver at Earth to slow down so that the Galileo fell in toward the sun and arrived at Venus, mind you, February of 90, got a gravity assist from Venus that put it on a trajectory back to the Earth. We flew by the Earth on December the 8th of 1990, got a precise gravity assist to put us in exactly a 2-year orbit around the sun, came back, and exactly 2 years later, December the 8th of 1992, got a final gravity assist from Earth and put us in a 6-year orbit around the sun, halfway around that orbit at the high point, 3 years after the assist. We're at Jupiter's distance, and Jupiter is coming along twice as fast as we were moving there and literally overtook us. In the case of the probe, ran into the probe to affect the probe entry. Now, I should mention, of course, that you don't get something for nothing. So each of these times we came by the Earth for a gravity assist, the Earth gravity accelerated Galileo, but Galileo, of course, pulled down the Earth and decelerated the Earth, slowed down the Earth. But it's in the ratio of the masses, so we didn't bother filing an environmental impact statement on that at all. So after the first Earth gravity assist, from 2.5 to 3.5 days after that, we took an image with our camera every minute for 24 hours, cycling through 6 different filters so we could make a color, the first ever color movie of the Earth making a full rotation on its axis. And here we have one of the frames of that movie, and this is South America, and you can barely see it. I'm going to illustrate for you how powerful our multi-filter techniques are for gaining information. This is a red stretch. And look at how much better definition there is of South America, and if the lights were a little lower, you could even make out the Gulf and Finger of Florida and so forth. So very powerful. Consider, by the way, that Galileo is the first spacecraft to have visited the Earth coming from another planet. It's true. Now, on this scenic route that we took, we used every opportunity to do science, and the number one thing was an asteroid encounter. So in October of 1991, we encountered asteroid Gaspra. This is the first image of an asteroid surface ever taken. Up to this point, all asteroids were but points of light in telescopes. Here's the first resolved image ever of an asteroid surface. And obviously, the guy had a tough life, got beat up pretty badly. On the second Earth flyby, the geometry requirements were such that we flew right over the North Pole of the Moon. And here's a shot where North Pole is right about here. This is a Terminator, obviously, and got some terrific imaging of the North Polar region of the Moon. I wonder if we could drop the lights a little bit. I don't think the quality is nearly what it might be. And then, 8 days after that Earth gravity assist, the Moon had revolved in its orbit to the point when we looked back at the Earth, we could see the Moon in the same frame. And we actually took images for 14 hours to make a movie of the Moon traversing the foreground of the Earth. We'll see that later as well. And it was a double header. On this crazy trajectory, we also went through the asteroid belt the second time and made an encounter with asteroid Ida in August of '93 and made the most important scientific discovery of the interplanetary flight, and that is found a moonlet orbiting Ida, since called Dactyl. And because we found that and have enough images of it to determine its orbit, we could thereby determine the mass of Ida. It would be impossible to fly close enough to one of these asteroids to sense their mass, but having this help us out, we could determine the mass, and the pictures give us the volume, so we got the density. That was quite a bonus, not at all guaranteed. Now, if you're not convinced the size of these asteroids, this is Ida and a freeway map on the freeway map of Los Angeles. Now, I think if you could get there, it wouldn't be any more difficult to drive on Ida than in LA. And I'm certain it would be safer. Everybody remembers July '94, the Shoemaker-Levy 9 comet fragments impacting Jupiter. Galileo, nearing its encounter with Jupiter, had the only position, it had a front row seat, the only piece of glass in the solar system, or the universe as far as we know, that could see directly the impacts occurring because they were just beyond the limb as seen from Earth. And here, in fact, is the W fragment taken by the Galileo camera. These are about 2 seconds apart, and you see the fragment just entering the atmosphere, here a full fireball, and now already receding in the space of less than 5 seconds. And our Galileo data was used very collaboratively with all of the Hubble telescope data and other Earth-based telescopes in analyzing the impacts of Shoemaker-Levy 9 on Jupiter. And this was the observation point. Here's where we were on our trajectory to Jupiter, and here's where Jupiter was. Now, here again, the arrival, December the 7th, 1995. No superstition, you can see. Notice that we had to release the probe 5 months earlier, July 13th of 95. The probe had no control system. The orbiter had to very precisely fire its thrusters and align the trajectory so that once released, the probe would hit the atmosphere exactly in its entry corridor, less than a 3-degree tolerance. Not only that, but after adjusting the trajectory, the orbiter had to reorient and align the spin axis of the probe precisely with what would be the entry velocity vector of Jupiter, spin up to 10.5 RPM and release the probe, and then the probe spun at that 10.5 RPM in that attitude all the way to Jupiter and arrived and entered Jupiter's atmosphere basically with the nose right down the flight path. And I submit to you that is by far the greatest rifle shot of all time. That was 80 million kilometers and spinning like a rifle bullet. So here is that probe, targeted probe trajectory into the atmosphere of Jupiter. Now, a couple weeks after releasing the probe, we had to do a big maneuver with the orbiter to get it deflected so it would not follow the probe into the atmosphere of Jupiter, which would not have been a good thing at all, of course. We used the main engine. This was our first use of the main engine of the orbiter after 6 years in space. Fired it for the first time, worked perfectly to deflect the orbiter to this trajectory, and you see it had to be deflected so it would overfly the probe as the probe was descending in the atmosphere of Jupiter. And so for 75 minutes, we listened and received data from the probe on the orbiter and recorded it for later playback. And then we were in a hurry to reconfigure. It took us 65 minutes to reconfigure, to then burn the main engine for a second time here at Jupiter for 49 minutes continuously to get captured into a Jupiter orbit, captured by Jupiter's gravity field. Here's an artist's rendering of the probe entry, toughest entry in the solar system outside the sun. If you're going to go to Jupiter, you're coming basically from infinitely far away, and by the time you get there, its gravity has pulled on you so hard that by the time you get there, you're going to be going 170,000 kilometers an hour. We hit that atmosphere at that speed, and this probe and heat shield, it took 228 Gs. It slowed down from that speed of 170,000 kilometers an hour to about 1,700 kilometers an hour in the space of 2 minutes. The aero shell, this heat shield, ablative heat shield, protected the probe here from temperatures at the stagnation point 25,000 degrees Fahrenheit, twice the surface temperatures on the sun. All worked perfectly, just beautifully, and the chute deployed and the probe descended, and we were able to get data. The probe sent us data for nearly 58 minutes and reached a pressure depth of 23 bars compared to a mission requirement of 10 bars. So we went more than twice our mission requirement in terms of pressure depth. And all 7 instruments on the probe worked beautifully and sent us just beautiful information about the chemistry of Jupiter, as well as the winds and other important things. About just about everything we were looking for, we found that it's more abundant than on the sun, and this all supports the accretion theory of evolution as the leading theory. Here in the illustration, of course, is the orbiter overhead receiving the data from the probe. There was no way to get the probe data directly back to Earth. It had to be captured by the orbiter and then later transmitted to Earth. And a moment ago we saw a blow up of this region where the orbiter went into orbit and again went into the largest orbit we dared go into. We didn't want to go a little to burn short. We had to be sure that we were captured, because otherwise we'd have a flyby, and that would have been a big mistake. So we went into a 7-month first orbit around Jupiter, and on the foundation of the orbiter's mission is on every orbit to target to a very close encounter of one of the Galilean satellites and use that satellite's gravity to change the orbit into the next one we want to travel, and so in so doing travel to the next satellite we want to visit. And in that way we progressed our way, bootstrapped our way through this tour that you see here. And again, just a couple weeks ago, less than a couple weeks ago, on November the 6th, we made our 10th encounter of the tour, the final encounter of this primary mission. And it's numbered 11 because you'll see there's no number 5 here in this progression. We were behind the sun and couldn't communicate during the 5th orbit, and that was all by design. And then finally, it was in the summer, by the way, that we took a long traverse out into opposite the sun in the magnetotail to measure the environment out here. And our fields and particles instruments detected the plasma sheet generated by Io to extend out beyond 100 Jupiter radii. Now, as Leslie mentioned, one of the most drastic things that happened to us on the way to Jupiter was our high-gain antenna could not be deployed. We tried everything imaginable and could not get the high-gain antenna to deploy. So what we had to do is we had to do massive reprogramming of the flight computers, the instruments, and the central computer and the attitude control computer, and basically take the best technology we had on the ground and fit it into computers that were nearly 20 years old on the spacecraft and build this new software. And we did it in the 3 years as we were flying toward Jupiter, and I actually finished it while we were in our first orbit of Jupiter, uplinked it to the spacecraft, so now the spacecraft could do a lot of the processing that we were originally planning to do on the ground. And in that way, very much improved the information rate to the ground, because over that low gain antenna, its signal, the power of its signal as received on Earth is 10,000 times weaker than was to be the signal over the high gain antenna. So we had to make up that the best way we could, and we did very many improvements to the Deep Space Network as well to enhance their capabilities, and we in fact increased by a factor of 10 their ability to get data from the spacecraft, and by putting all the software on board the spacecraft, we increased our information by another factor of 10. So fully two orders of magnitude were achieved. And the way that we have run the mission then is that on every orbit close to Jupiter, for about 7 days, we do our encounter sequence, which includes taking images and other high-rate data of Jupiter and the targeted satellite and the other satellites. And then for the balance of the orbit, that is typically 1 to 2 months long, we incrementally read the tape recorder, compress the information, and send it down the downlink, and have to get as much of it out as we can before we get around to do the next encounter. It's worked beautifully. It's worked greater than any of us could have hoped for. It was a wonderful solution. Now, we have almost limitless at this point beautiful images of Jupiter. So now I get to show you my favorites, because there's nowhere near time to show you all that we'd like to show you, but I'll show you my favorite images, and again make an apology. I wish that we knew how to convey the other equally important information we're getting from the Jupiter system with our other 10 instruments, which are also working and providing excellent results. But we just don't have as good a way to convey that information to you, but please accept that those things are working beautifully as well. Here's the red spot. Remember, in Earth diameter, we're seeing an oblique view. So this is the longitude direction where you can put Earth about 3 times across there. This is a so-called hotspot on Jupiter. The Earth would almost fit into this region right here. It's not the area where the probe entered, but it's very similar to the area that the probe entered. And so these hotspot regions, they're like deserts, if you will, in the Jupiter atmosphere. And it's characteristic of a very violent circulation, vertical circulation pattern that we have at Jupiter. And a very interesting point, the probe, as many of you will remember, found surprisingly little water vapor. When we did recalibrate the instruments for the high temperatures the probe experienced at the end of its descent, that would actually kill the transmitters and ended the mission, we found that we were seeing about twice solar abundance of water at the end of the descent in these spots, but very little water early on in the descent. I'm delighted to tell you that in the water sounding that the orbiter has been doing for the last 1.5 years on Jupiter, it has determined that there's a tremendous variability of water around the planet. And in fact, typically, there are factors more than solar abundance of water in the Jupiter atmosphere, but in the particular place, by happenstance, the probe went, it's very dry. Pardon? Okay. And here's a similar region Not the same one and not where the probe went, but a characteristic of that. And this is in false color. Remember that using the filters for stretching the color? So this is a stretch color image of that region. This is what your eye would see, natural color. And a similar area of Jupiter near a belt zone boundary, again in a bit of stretch color. And here we have a couple of well-established ovals near the equator and a new cyclonic feature. And again, the Earth would just about fit into these. It's a little bit too big to fit through there, but it gives you an idea of the size of this place. And again, natural eye color here. Aurora borealis on Jupiter. That's what this is. It turns out that the longest magnetic field lines that close on Jupiter, start at Jupiter, go around in space, and come back to Jupiter, that's where the charged particles get the greatest acceleration. And when they bombard back into the Jupiter atmosphere, they excite it and cause this aurora borealis. And it's a very, very dynamic and very analogous to what's going on the Earth. And by the way, it's standing off the what we call a surface, which is a misnomer, of course, but we define 1 bar pressure as the reference surface on Jupiter, and this stands off a couple hundred kilometers from that. Io, the pizza pie, as promised. Our best full disk image of Io. Tremendous changes in Io since Voyager, and Galileo has determined about 20 new hotspots on Io. Here's a discovery picture. You can see the plume of a volcano here on the limb, and that's a blow-up of it. And here's another volcano right here that's blown up here. And this is actually the shadow cast by the plume. These plumes are typically 100 kilometers high. Can you imagine something 60 miles high? This is one of our most recent releases. This is one of the volcanic areas on Io. And this image was taken in April, this one in September. This eruption here, this is about the size of the state of Arizona. It's about 400 kilometers across. So imagine the dramatic things that have been happening there on Io in this past 5 months while Galileo has been watching. Europa. Europa is clearly our darling at the present time. The prospects of liquid water under the ice crust are very, very exciting. One of the early images taken on one of the early encounters, not of Europa, but at a long range, showed these remarkable surface features, what we refer to as triple bands. And this is a very large-scale image, about 1,000 kilometers across. And this was one of our first clues. We looked at this and we saw a jigsaw puzzle of ice plates. Clearly, you can imagine shoving these plates back together, closing these gaps. Very good evidence. There was some fluid bearing there at one point. Another image of Europa surface. Quite remarkable structures. And this, in fact, is the image that we showed to Pope John Paul. We can't date exactly when these things happen, but you can quite easily see the scenario, which events followed which events. You can see how this broke up this other pattern, for example. And this is just a closer view of it. And now we're closing in on the smoking gun. This, what turns out to be a field of icebergs, in our belief, is this. And we call this a smoking gun because this is what leads us to believe, in all likelihood, we have liquid water on Europa. It goes like this. There's virtually no craters here, so this is an infant surface in geologic time. So when this surface was formed, which could have been tens of millions of years ago, but that's an instant ago, compared to the 4.5 billion years age of the solar system. So when this surface was formed, even though we took a picture of it tens of millions of years later, when it was formed, what you had was icebergs floating in a liquid water ocean, and then the water froze. It's inconceivable that that water could have completely frozen out in this instant of geologic time. since we took that picture. And just to give you a better understanding, better feel for the size of things, this is that image compared to San Francisco. So there's the Golden Gate Bridge, for example. And we also have another quite interesting feature. We call this our puddle on Europa, which is about 3 kilometers across, and evidently fluid that has risen to the surface and obliterated, covered up all the surface features, most all the surface features. And here's the comparison with San Francisco again. So it would have been quite a flood at the Golden Gate Park. 2 kilometers across by about 300 meters high. Imagine a structure like that. That runs for about 1,000 kilometers across the surface of Europa. Now, I'm showing you these in the order from Jupiter on out to Callisto, but not in the order taken. This was one of the first images that we took. This is the Voyager image of the particular area. This is Galileo's image of that same area. We knew we had a winner. We fulfilled our promise. This is just spectacular. The Voyager imaging told the scientists that there was fluid flows that formed these surfaces. The minute they saw this, they said, nothing doing. We've got Ganymede quakes going on. We've got plate tectonics is what's forming these features on Ganymede. And here are 4 of our early frames of Ganymede superimposed on the best Voyager coverage that you see there. Very, very dramatic improvement. And this, interestingly, is called is a dark region on Ganymede called Galileo Regio, and about a 30-kilometer diameter crater here. And not to be outdone by the Mars people, we have a face right here, and we have a man with a turban on his head right here. So we also are in hot contest with them, of course, to find life on Europa before anybody finds it on Mars. We'll see how that comes out. And many of us might be around to see that happen. Callisto, a big surprise at Callisto. We thought we'd see craters at every resolution. Instead, we see some sort of powder-like debris all over everything, covering the fine-scale features. No idea where it came from. It's a major question to be resolved. By the way, the feature you saw there could well have been formed by a Shoemaker-Levy-like impact, those scallops you notice. This is a scarp. Again, you see the powdery substance. These images have a resolution of about 30 to 50 meters. Now, although I told you I don't have a good way to show you things other than images, the one thing we can convey is with our gravity sensing through the Doppler radio tracking, we can determine the interior structures of these satellites, and we have determined that Ganymede and Europa, for that matter, have a 3-phase structure, a metallic-like core, then rock, and then ice, and in the case of Europa, liquid water in here, and then an ice shell. Callisto, we've determined to be uniform, no magnetic field. We have determined a magnetic field at Ganymede and a magnetosphere around Ganymede. So we know that Mercury and the Earth are magnetized. Ganymede's the first moon in the solar system determined to have a magnetosphere. Again, Callisto not, the moon not, Mars not, we thought, but Mars Global Surveyor is reporting some sensing of local magnetic spots on the surface of Mars. So we might have to change our mind about that. And Io is to be determined. And here's part of that to be determined. Delightfully, we have a 2-year extension. We're going to operate Galileo to the end of this millennium, at least provided the spacecraft stays healthy, to December the 31st, 1999. And by golly, next month, we're going to have the first of our encounters of the Galileo Europa mission. On the 16th of December, we'll have encounter number on the 12th orbit. It'll be Europa 12, so that's the 11th encounter of the mission. 8 consecutive encounters of Europa. We expect to get over 5 times the imaging data on Europa that we've gotten so far through this campaign. And then 4 encounters of Callisto, not to look at Callisto, not to measure Callisto, but to use Callisto as a gravity assist body to lower the perigeo, the close point to Jupiter, so that we can once again go to Io. We only went there on the way in and couldn't take our images because the tape recorder was giving us problems. So we hope to get back there, and the spacecraft willing, we will do a pair of encounters with Io in the last quarter of 1999. And then, if the spacecraft's still good, we intend to operate it indefinitely, but in a very limited mode. So, welcome to JPL. Now, how's the time, Leslie? Good. So now, what I want to do now is show you some of those scenes that are promised in the video. So could we go ahead and show the video, please? And this should be up momentarily. Now what we're going to see, we're going to run the video, please. Hello? Ah, there it is. Remember, this is taken by the first spacecraft to visit the Earth from another planet. But that doesn't look like what I'm hoping for. Please stand by. Well, the last time I did this, I said, okay, let's have a question. We'll get a question in before we get this going, and then right away it started. So we'll try that. Anybody got a question? Quick question.
Solar panels, are they driving the
No.
vehicles back?
No solar panels. You can't operate a spacecraft much beyond Mars with solar panels. We use RTGs, radioisotope thermoelectric generators. So the RTGs that you saw on the end of the boom, or two booms, and you can also see next door, they put out about, at mission start, about 500 watts of electricity. The whole spacecraft's run on that 500 watts of electricity.
Continuous?
Yeah, it's continuous output, but of course it degrades very gradually, and we're down to about, I think, 470. Actually, we started probably around 520 and down to 470 or 60, something like that. Same as Voyager, same as Cassini, same as Ulysses. Anything operating out there, you need to take your energy with you. You can't. How we doing on playback? Okay. Try it again. Next question. There's a question back there.
Where is Voyager right now?
Voyager is, somebody can help me with this. To order of magnitude 100 astronomical units, I think, from, who can help me with this? Somebody here surely knows, but it's 100, 125, 110. Come on, who's good? Don't leave me up here alone.
Dr. Clarke's on the line.
Oh, is he ready? So we have something more important to do. We're going to talk to Arthur C. Clarke. But we'll get you that answer. But believe me, it's very far, and we're still tracking both Voyagers routinely. Are you going to? Yeah, I do.
All right, thank you. Sorry about the little snafu, but we have Dr. Arthur C. Clarke on the phone from Sri Lanka, which is near India, if you're not familiar. And so we didn't want to keep him waiting. We wanted to just move on ahead. So what I'd like to do very quickly is introduce him to you. He was born in Minehead, England in 1917, which means he's about ready to celebrate his 80th birthday. He now lives in Sri Lanka, like I said, and he was the first person to be granted the resident guest status there. He is a graduate and fellow of King's College in London and chancellor of the International Space University and the University of Moratuwa, which I hope I said correctly, near which the government has established the Arthur C. Clarke Center for Modern Technologies. While he was serving as a Royal Air Force radar officer in 1945, he published his theory of communications satellites, most of which operate in what's now called the Clarke orbit, with an E. The impact of this invention on global politics resulted in his nomination for the 1994 Nobel Peace Prize. He has written over 70 books. He shared an Oscar nomination with Stanley Kubrick. Those of you who are old enough to remember, I certainly do, for the movie based on his novel 2001: A Space Odyssey. And his many honors include the Marconi and Lindbergh Awards, as well as 3 Hugos and 3 Nebulas for his science fiction. And in a global satellite ceremony that happened a couple of years ago in '95, he received NASA's highest civilian honor, the Distinguished Public Service Medal. So as you see, we have two very honored guests with us tonight. In 1996, he went to Beijing to receive the International Academy of Astronautics' highest honor, the von Karman Award, which is the name of the museum you're sitting in now. Dr. Clarke's recreations, he likes to quote, are scuba diving in the Indian Ocean, looking at wrecks with his companies. It's called underwater safaris. He likes to look at the moon through his 14-inch telescope, and likes to play with his dog Chihuahua, or his Chihuahua Pepsi is his name, and he has 6 computers. And for those of you who don't know, he wrote 2001: A Space Odyssey. I have a couple out here that just been re-released: 2010, Odyssey 2, 2061, Odyssey 3, and just this year has come out with 3001, A Space Odyssey, the final Odyssey, excuse me. And we're honored and very privileged to have Dr. Clarke with us, and what we have asked him to do is just to give us a rundown of what was his interest in Jupiter. Before we go on to that, however, we wanted to let Bill O'Neill say hi to Arthur.
Hello, Arthur. I am delighted to talk to you again, and recalling our conversations in Beijing, I wanted to report to you that Galileo has done an awfully good job since we talked. And with respect to the one fear that you stated, I can tell you that I've kept the promise. There are no Yankee go home signs on Europa. And I'm equally delighted to tell you that our Hal has behaved well all year long. So we're very anxious to hear from you. Welcome.
Well, very nice to talk to you again. I'm a bit husky at the moment, but I hope that I'm intelligible. Am I?
Yes, you are.
Right, and of course this isn't going through the old-fashioned satellites, but by fiber optics, so there's no time delay.
Isn't that wonderful?
Well, now, you mentioned my 80th birthday, which is getting so complicated now I can't keep track of it, but Discovery Channel is doing a 3-hour, believe it or not, 3-hour program on or around my birthday. I don't know when it's going to be broadcast in the States. It's going to be the 14th of December in Europe, and they're negotiating with the American branch of Discoveries, and so sometime around mid-December, if you can bear it, you may have 3 hours of me. Well,
we'll be glad to get it.
Okay. Now, I've been told, first of all, I must make it quite clear that what I'm saying now is Arthur C. Clarke and doesn't in any way reflect NASA's feelings on the subject. Well, sometimes I wake up in the night screaming, thinking that I'm the NASA administrator desperately searching for signs of intelligent life in Washington. Anyway, we were supposed to be talking about Jupiter and its moons. Now, in 2001, in the novel, we actually went to Saturn, and much of the action took place on Iapetus, which we'll know more about, of course, I hope, when Cassini gets there. The reason why we didn't use Saturn in the movie is rather interesting. The special effects department decided that Saturn didn't look real. No one would believe what we showed. And, of course, if we'd known then how much more fantastic it really was, I'm very glad that we didn't attempt to show Saturn as we thought it would be in 1965. Because, of course, now we know Saturn's ring system is absolutely unbelievable, and I'm sure a lot of celestial mechanicians are still going crazy over it. So we went to Jupiter instead of Saturn, and indeed I'm glad we did, because then we found out a lot more about the moons of Jupiter, which inspired 2010, and later I went back, of course, in 3001 for a more detailed examination. I wrote those books, of course, not knowing as much as we now know about the Jovian satellite system, specifically Europa. And it's a very good article on this subject in the December Sky and Telescope, which I'm sure many of you have seen, about the possibility of life on Europa. I am particularly anxious to see what Galileo does in its future flybys as it gets closer and closer. And as many of you know, I'm extremely intrigued by that extraordinary image that is sent back, reference PIA 00588, which I have in front of me at the moment. And now, for those of you who haven't seen this image, which may be one of the most historic that's ever come from space, it shows the fantastic broken European landscape with lots of jagged ridges and superhighways and things meandering across it. Really weird, but nothing, you know, unnatural until you look at the top of the image. And here's this absolutely straight line, more than 100 kilometers long. But not quite straight. It bends slightly where it goes through one hill and another. And I mean, I can't imagine how any natural phenomenon could produce this. And there's another almost equally straight line at the bottom of the image, but that does some slight curves. So completely uniform thickness and quite different qualitatively from all the other lines that are zigging and zagging over the landscape. And I am quite serious when I think that I can't think of any natural explanation, though I suspect there must be one. My tentative theory at the moment is that Europa is inhabited by a race of demented highway engineers fighting a losing battle against continental drift. Well, I think that's enough for the moment, so I'll be over to you.
Thank you so much, Dr. Clarke. We have over 300 people here from the LA area who have just been waiting to hear you, along with Bill. So why don't we give Dr. Clarke a round of applause.
Happy birthday! Thanks again, Dr. Clarke. And now we have about 5 minutes for questions from Bill. So you would just like to field them yourself? I should ask the questions?
No, yeah. You guys got to take a test now. That's right. Now, what I need to make sure is that we've got the floating mic available, and here it comes. So if you have a question, please raise your hand.
What happened to our video?
I don't know. Please raise your hand and then wait for the mic to come to you. We will break it off after 5 minutes, and then we'll restart after the tape, okay?
Oh,
so, 5 minutes worth of questions.
I just heard Arthur Clarke say something about a line going across and suggested perhaps it's not is it working now? That he can't think of a natural explanation. Have any of your scientists have any natural explanations for that?
Not that I've heard, but remember he said he thinks there probably is one. But no, I can't get them very excited about that line. Do you have anything to add to that? Yeah, it does look like a freeway, but it's quite unique, and we'll have to see, and almost certainly we'll see some of that in the next year in the Europa part of the GEM. And by the way, this encounter in December coming up is the closest encounter for Galileo of all time. It'll be at 200 kilometers. So imagine that. We're 500 million kilometers away. We're going to fly over this moon at 200 kilometers altitude.
How hot is Jupiter?
Well, it depends where you measure it. At the very top, it's not very hot. Where the probe failed was about 100 degrees centigrade, so about the temperature of boiling water. But as you go down, it gets much, much hotter, and tens of thousands of degrees if you get far enough down. And I should let you know that our probe only went a very shallow distance into Jupiter. And where we did measure, as I say, was about 100 centigrade. But it's much, much hotter than that as you go in deeper. And in fact, although the probe was not working anymore, we know from physics that the probe was melted and vaporized. And now it's just its elements are a part of the Jupiter atmosphere.
Another gentleman mentioned before about using solar energy, and you said it was too far away to do that. Jupiter gives off more energy than it receives, though. could we use Jovian power once it got close to Jupiter to motor the spacecraft?
No, it's nothing.
just-
What is said is that, yes, it puts out more energy than it receives from the sun, but nothing like what it would take to get electrical power to operate a spacecraft.